Fl. So here, even here, I don't know what is the minimal degree. The attempts which we made there, okay, they are not. So now I think that we have enough combinatorial methods to prove some structure theorems. So I want to go to the theorem of Kaplanski.
Like, is it clear that the growth should be quadratic? Like, can prove? No, not even.
Okay, you see.
Well, it looks as like n squared n minus 1 squared.
Okay, here you can write this is maybe n squared minus 3. Maybe this is n squared minus 3n plus 3 minus 2 maybe. Divided by 2.
Yeah.
This is the function which for n1. This is 4 minus 2 for n2. This is okay. Maybe this is the function.
Yeah.
But you see, I don't know. The first feeling is that it should grow quite fast by some arguments, but these arguments, they are not mathematical, they are simply some belief. So now I go to the theorem of Kaplanski. Which was in 1948, and in this paper also Kaplanski introduced for the first time the notion of polynomial identity. So he defined here what is a polynomial identity. So he also, Kaplanski, introduced the notion of polynomial identity. So it was not only the father of the theory, but also the godfather. Maybe. And the theorem of Kaplanski, before to say it, I defined something. So also before, you see, all the time I speak about algebras over a field. And you can define also PI rings. So this is a remark. You can speak about PI ring. When, so you start with the free associative ring. You take a polynomial here, and you say that this is a polynomial identity for the ring R if f of R1 Rn equals 0. Of course, this is a very nice definition. But the problem is that if you have, for example, twice x1 equals 0, this is also a polynomial identity. But this is not very nice because you have that here this holds also for the free algebra over the field with two elements. So this is not a real polynomial identity from the point of view of the theory. So in order to avoid this, one says that here the requirement is that f x1 xn is multilinear and has a coefficient equal to 1. So here the coefficient is 2, so this is not a polynomial identity.
So it's sufficient to have the greatest common divisor of all the coefficients equal to 1.
Maybe you can do this, but okay, this is you can find you can do this, but you need a multilinear to be multilinear, so you can do this. But so instead to have this one, I prefer to speak about algebras with polynomial identity. But most of the results, they can be restated for rings. So the algebra R, so this is the definition, R is an algebra. It is called primitive if it has a simple, faithful left R module. So this simply means that I think that even in the commutative people, they know that in the non-commutative case you have left modules and right modules. So here you multiply the elements only from one side. And this means that the module, simple means that the module has no submodules except the module itself and the zero module. And there are no elements of the algebra which annihilate all the elements of the module. So an example is when R, this is the matrix algebra over division ring D. So D, this is a division ring. Okay, over a field, over K, division algebra maybe. And it's clear that if you consider, for example, the n-dimensional vector space over D, this is a simple module, and the matrices, they have a natural representation here. So the simple module, faithful module, is the direct sum of n copies of the field with the natural action of the matrices there. There are also some examples which are not so trivial. Another example, you consider all matrices R consist of all matrices of the following form. Here you have some block of matrices, and here you have the same diagonal element. And here you have 0, 0. So you have a finite block of elements, and here you have the same element. Okay, this is infinite. Of course, this is an algebra, because if you take the sum of two matrices of this kind, or the product of two matrices of this kind, you get a matrix of the same kind. And in order to see that this is the case, that this is really to have the corresponding faithful module, you simply take the infinite sum of the infinite dimensional vector space over the field. So this is really the case. And I simply want to mention a fact which is, this is a lemma, this is a sure lemma I think, that if M is a simple R module, then the set of all endomorphisms of M as a module, or these are all alpha, which are endomorphisms of the vector space M, with the property that alpha Rm equals to R alpha M. Maybe I should put this way. For all R in R and all M in M, this is a division ring. So this is something which is well known, and of course this is an exercise in ring theory. But now the next definition I want to give, this is the definition of a dense subring. So if definition. If M is a faithful R module, and D, this is as a division subalgebra of the algebra of endomorphisms of the R module M, and if for all linearly independent M1 Mk in M, linearly independent over R, or D. They exist N1 and K in M, not obligatory linearly independent. There exists some R in R with the property that R of Mi equals Ni for all i's. Then R is called dense in the endomorphism algebra of R, of M over R. So this means that, assume that you have a division subalgebra of the algebra of endomorphisms, you have a faithful R module, and if you have linearly independent elements over D from the module, you can send these elements to any k-tuple of elements, multiplying by element of the ring. Then this means that the ring is dense in the algebra of endomorphisms in over D, of course. Sorry. And in the special case when, so if M is a simple faithful R module, then we have that this object here so if maybe I should write this in another way. So if R is dense, so if R is dense in the endomorphisms of M over D, then of course M is a simple R module. Because why this is a simple R module? Because if you take M in M, then and not 0, and N is any element from M, then this element is linearly independent over M. So over there, so this means that we have that there exists R such that Rm equals N. So this means that you have no proper submodules, because if you take any element which is non-zero, you can send this to any other element. So this simply means that if the algebra is dense, then the corresponding module is simple.